Welcome. I'm Raf Vescovi, Rafi, and I'm going to talk about Gladier, which is the Globus architecture for data-intensive experimental research. I know that that's a big name, and this presentation will take a 90-degree turn over the more technical presentations that we had. So before I go over the more technical parts, let me just really quick tell about the motivation of Gladier. Like if you see the green curve is how our computers, like our computer resources are growing. So that's the Moore law. And if you see the red curve, that is how our accelerators are growing. So that means that the data that we are generating into these very, very large scale experiments is growing much, much faster than our computers can handle. So if you saw Matthew's presentation yesterday, like the same is happening with electron microscopy, the same is happening with like even tabletop sources. And what we have is that we are tying resources, like we have big resources like the advanced Poisson source, and we are building big computers, but these two kinds of resources have completely different people, or they have different research statements, they have different entry curves or skill requirements, they have different allocation systems, usually like scientists, they need their result right away. While we in computer science, we can think about like long-term or submitting hundreds of jobs and waiting for the allocation. And like all these small differences that make it very hard for us to translate like this very high-end, high-performance computer science into the everyday life of like researchers. And the same, like researchers trying to explain what they do, so we translate their code into something that runs really fast. So what is the canonical research automation? Like for pretty much every experiment, you capture data, you stage this data somewhere, you transfer it where it's going to be transferred, where it's going to be analyzed, sorry. You maybe give some feedback to the user, and then you catalog and publish it. The reality is that this is only as simple as the amount of data that you acquire. So we keep pushing over having better experiments and having better processing, but there is there's this barrier of integration between facilities that is very hard to go through. So basically, like on a normal experiment, like you have your acquisition, your processing, your visualization happening at the same place. And that for many reasons, but the main reason is that the people that are doing electron microscopy or doing X-ray science, they're not used to opening a terminal. And sorry if someone will get offended by that, but like the users that I had when I was an experimental scientist, they were not used to opening a terminal, SSHing into a resource, and then SCPing the data, and then transferring, and then they realize that they don't have a notebook or they don't have a way of seeing this data, and the experiment stalls. So the problem is now you add a remote location and you need to process this data. So you need to transfer the data, you need to transfer the instructions, and then you need to send things back. Great. So we saw all these talks about funcX and how funcX can make like this transfer of instructions.
The time is 3:45 p.m. Time to start wrapping up your workday and plan for dinner.
Sorry for the interruption. Google is reminding me that I should stop working. So, so we saw that funcX makes this transfer of instructions and this triggering of the processing incredibly transparent to the user. So, you're going to create your hello world function. Your hello world function will give you an UUID. All you need is to wrap it, install your funcX client into your resource. You can use your Kubernetes cluster. You can use whatever function you wrapped around funcX. And now you have this incredibly transparent way of processing data, right? The problem is like that creates this onion of layer upon layer where you have your HPC resource. Now you have Parzo like taking care of like the jobs, and you have funcX on top of Parzo. You have the transfer service moving data around, and then you have your action providers like Tyler showed, extracting data or making sure that user inputs are going back and forth, or that your portals are coming back in a user understandable way, like the MDF. So Globus created Automate, and what Automate is an orchestration system around all these action providers. And pardon, it's not called Automate anymore, it's called Globus Flows. I'll fix that in a second. What we've noticed when we started using Globus Flows is that is still don't help the user, because that needs a lot of computer science. Like it needs a lot of like understanding the JSONs and all the IDs of everything. And the user at some point, you will see on Hemant's presentation, he gives up and goes back to using his workstation. So what we wanted was to use the same environment for everything. Luckily, like Globus gives us the authentication service that gives you data transfer very easily, gives you like shares and searches. With Funtex, give you the remote execution. With MD, like you have portals that you can use with like the search index, like the MDF. But on top of that, we want to give you a way of getting all these jobs that you transform into a Funkex, into an incredibly effective parcel submission. And we wanted to get you to tie it to the user experiment. So what we did is Gladiator. And basically is we want to accelerate and simplify the flows to bridge the instrument with the computing facility. So basically is bridging the very basic user, the guy that, the biologist that is going on the beam line, or the biologist that's going on an electron microscope, with the very end of like our processing, which is cataloging, like making this data after all the creation and processing into a portal. So we're going to use Globus Flows, as I said. And what is Globus Flows? Is a chain of actions. So if you're using Amazon step functions, you are like 90% overusing Globus Flows. Basically, every action becomes a step function, and you can create chains of step functions that interacts with an action provider, an HTTP action provider, and use whatever resources you have, like transfer or Funkex or a web form or a description or a sharing of policies or an ingestion into a portal, into a single chain. So that gives you the opportunity to trigger and to tie experiments together. So the same way that this will give you the opportunity of tying jobs from Funkex, you say like, well, this job is over. I wanted to publish something, but I don't want to have to write different Funkex functions or write like a gatekeeper to see if my job is over. What I do is I create 2 blocks of data or 2 blocks of Funkex functions, and one executes when the other one finishes. And I can see over the web like how this is happening. So if you are a Globus user, which I'm pretty sure all of you are, like, can you go now to your Globus interface? You will see that you have these buttons called flows here. And basically, flows will give you the status of like these flows that you started and how they have been doing. Now, what we were the guinea pigs of this service. We were trying to get that to be used by the everyday user. And what we noticed is that this is how a log looks like. And that is hard to read if you know what's happening. that becomes unreadable if you don't know what's happening. So we decided to create a black box around everything. And that black box is what we call Gladier. So what Gladier will do for you is to make sure that your Python package that have your local functions, that have like the definition of your containers, that have the configuration about your funkex endpoints, and we'll register these functions with the funkex server. Like, so we'll make sure that it knows all the IDs of like the version of the function that you are using. We'll register the flows, like with the flow service. We'll do all the authentications for Globus for you. We'll make sure that it validates the input. We'll make sure that the metadata that comes out of your chain of events makes sense for whatever you're doing, and raise the errors through the parser errors or the funkex errors or the transfer errors in a manner that the user can actually interpret it. And the way that we are going to do that, as I said, is by hiding under the hood all these calls or all these Amazon stack functions that will be interacting with funkex or parso or the Globus automate. So we are calling this the Gladier tools, sorry. And the Gladier tools are these boxes or these actions that can be tied together on the Gladier base. One thing that we also can do is that we can move data around through different services without having to SCP or to SSH into the machines. So not necessarily you can just do Globus, but if you have a resource like Eagle now at Argonne that is tied to Polaris or Aurora or Theta, and this resource can publish the data through HTTPS, you can now make your flow see this data and interact with this data without you having to give explicit access to users or to people. So this is how a flow looks like. And like we created our funkex endpoint, we now have our funkex like function ID. We have the ID of the flow, we have the ID of the run, we have the ID of the result, and that is unfathomable for the user to take care of. And when I say the user, again, I'm not saying a computer scientist, I'm talking about the binline scientist that is sitting and stressing about the motors at the binline, about the biology user that's coming. So we created a very, very high level interpretation of things, which is to create a chain of events. All you need to do is point to the Gladier class that wraps around your local function. And Gladier will make sure that if this function is tied to a container definition, or is tied to a resource definition, or is tied to a parso config file definition, Gladier will make sure that it goes to the correct place and is executed with the correct version. So you see, like, this is how a Gladier flow looks like. And once you create these tools, it becomes a class for you that you can just go on a Python notebook and put the inputs that you want. And as long as you make sure that the data locality is correct, in other words, that you're sending the raw data to where you're sending your funkex definitions or your funkex calls, like Gladier will execute everything remotely for you. So some examples, again, as I said, this is more like a user side. We have the APS, they are generating data. This data is being transferred to RCF. It actually gets processed at RCF. The results are plotted, sent to Petrel, and then published over a portal without the just beamline scientists having to press any button. This is how it looks like in reality. Like you have this chain that is using a Globus transfer, and then a funkex function, and then another transfer, another funkex, and then ingesting that into a portal. The interesting is that now you can tie these Globus services to whatever you're using. So if you have a submission system, if you have already like your own parso endpoint or funkex endpoint, or you even have your own trigger system, like the data management at the APS, you can tie to the Globus flows or to the automation flow of Globus, because all you need is to create this chain of step functions, register that in a Globus, and then invoke them when you wanna do it. So we have showed this in a more, let's say, heavier, in a more batch way, which is we are doing that on a serial crystallography experiment that is happening real time. So we are acquiring data at the order of gigabytes per minute, and we are transferring it and analyzing the data real time, generating refined structures and publishing it on a portal that the user don't actually need to even think about what is happening, because some beamline scientists told us, well, this is the image that I want to see. As long as this image is created real time, I don't care about what happens under the hood. These are the codes that I use. Now, this adds the ability for us to create self-steering experiments. And what are those self-steering experiments? It can be a polis, like I generated data, I have these, I'm looking to different resources that have different funkex endpoints, and I choose the resource that is going to be better for my data, or I have a funkex function that will be better at GPUs, so I steer the data to this particular location. But more than that, I have an experiment that is real time telling me I have enough data, I have enough quality to continue, or I don't, or I have enough overall quality, so go into the beamline and change your sample, or you're doing very bad, like abandon this sample. So basically we are using all these systems, everything that we are doing to give real life steering or real time steering to real life applications. And one of the examples of this being used is on the fight against COVID-19, where we process the proteins, or we refine the proteins real time using Globus flows and funkex and transfer and radio. So other examples is transferring data from Slack, from Stanford all the way to Argonne, like merging it with DL Hub, or actually like doing real-time simulation of the data and then comparing this simulation with the acquired data and sending feedback back into their experiment at Slack. So we have many other experiments, like lithography generates real-time, like big, different scales of parso execution for reconstruction of like nano resolution tomography. We also have the high energy X-ray diffraction that Hemant is going to present next. And we can think about like an even weirder future where we have all these services, and instead of a human steering the experiments, we actually have the experiment self-steering. I know that that's not the correct crowd, but because like I was a beamline scientist, that for me is a pretty scary scenario where now we have like the computers doing so much of the heavy lifting and me only having to worry about this HTTP portal and then a robot doing my job. So what we want to provide is a way for the low-level scientists to integrate with funkex, integrate with parso, integrate with the HPC facilities without having to know all the computer science background that we have. So, and more than that, we want users to write these functions as they would write locally, and then be able to share the functions between people. So if you think about a funkex or a parser executor that have a very agnostic or a system agnostic Python description, now me, the tomographer from the APS, I can write my routine, submit it to the funkex server, and then someone else at Stanford or Japan can get my definition on funkex and build on top of it. We also have a collaboration with Braid, which is this DOE ASCII project that is trying to find these rule-based engines to support this continual computing, or in other words, like this decision-making, this ML modeling to steer the flows in real time. And I'm not going to go over it because I'm already over my time, but I also pasted on the chat. If you want to try Gladiator and see really what is under the hood, please go to jupyterdemo.globus.org. When you go into it, you will see that there is actually other demos too. The one that you're looking for this particular presentation is the one called Gladiator Flows tutorial. And honestly, it's a pretty interesting flow, because it will end up on you creating your own portal that injects the data for you. And that is pretty much it.